how this works. Okay, hello. We're going to look at relative error and percentage error, and this is part 1. So this is all new to me. We'll see how well this works. So here's the idea of relative error. Suppose you had your x-axis and you measured x was 20. And that's the actual. This is the true value of x. But somebody else comes along later and they measure over here and they measured 21 by mistake. Okay, so maybe it's the length of a room or something, and they made a little mistake. What we would call the actual amount of error, well, they're off by 1. So this is the actual error. Okay, let's try to write this here. Actual error. And something that we call relative error is to say, well, the actual error you're off by 1 compared to the true length, which we know is 20. This is what they would call relative error. It's kind of relative to the actual measurement. Okay, and if you wanted to, you could turn that into a percentage, percent being over 100. So you just figure out that top number and you get, oh, that would turn out to be 5 over 100. And this is what is called the percentage error. Okay, that's the idea behind it. Another way to think of this is that the distance that you're off by here is kind of like saying that's your change in x. And your 20 over here, that's actually the true x value. So you could think of this as the amount that you're off by along the x-axis compared to the original x. So this is relative and percentage error for the x's, and we could do this for the y's as well. All right, let's see here. I wonder how I can keep this whiteboard going here. Hold on, I gotta play around a little bit here. So, clear all drawings. Okay, let's try that. Yeah, I guess we just clear it all. Okay, so now I'm going to say, well, what if I was looking at y numbers? And it might be my y-axis, and maybe the actual y value is something like 400. But we came up with a mistaken y value at, say, 440. Okay, so if you're looking at, for the y's, your change in the y values here, or delta y, is 40. And compare that to the original actual y value of 400. There's your relative error for the y's. And if you want to turn that into a percentage error, you just put it over 100. So this would be the same as 10%. So that is your relative and percentage error for the y's. Okay, so pretty much the same idea as the x's. Now here's where the calculus part of it comes into the picture. So let's clear the screen again, and then we're going to clear Ultra. All right, so way back when, now let's see if I can draw this a little bit better here. Let's see, shapes of some kind. Draw, there we go. Let's put a line here. So way back when we looked at our graphs and we drew your kind of standard function, we had some kind of function that went like this, and that was f of x. And we said, oh, there's a point x down here, and then that had a y value as well. And we said, well, what if we're off a little bit and we're way over here? So this is x plus delta x over here. And of course, it also has a y value somewhere up here. And what we did was we had this distance. I'll try to draw this in as neatly as I can. to here, this is your delta y. So that's your change in the y values, because this point over here has the actual y value, or f of x. And this point here is off because of the error we did in the x's. So we're off by delta y. And so we had our tangent line. Let's see, I'm going to switch to the line draw thing. See if I can do a decent job of it. So we had our tangent line looking something like, something like, hold on, I hit undo here. Let's try that again. Undo. Undo. So we'll try that again. Okay, so here comes our tangent line, sort of like that. And what we did was, we said the distance to this point, up to there, that's actually what we called dy. And the idea is that dy is very close to delta y. So the relative error technically is this. And suppose you can't figure out delta y, you could use as a good approximation, so we say approximately dy instead of delta y. So this is what we end up using to figure out the relative error. And the way we figure out the value of dy is quite easy, because we have this little relationship. Dy by dx is equal to the derivative f prime of x. So if you multiply the dx to the other side, this is what dy is equal to. The derivative times dx. Okay, so now if we put all that together, see, I wish I could extend the page here, but I'm not sure if I can. What this does. Uh-oh, I think it just, oh, I see, yes. Oh, there we go, it's a new board. So now what I'm going to do is I'm going to take this information and the part that I've circled up here, oops, let's undo that. Put extra, okay, so this part here, I'm going to replace dy with what I have down here, which is f prime times dx. And so here's what we end up with. So let's see if I can go to the other board. So here's where we're going to end off. We would like to find this relative error. Okay, and we can approximate that with dy compared to y, and that is equal to the derivative times dx all over y. And if you want, you could even just put in here that y is the same as f of x. So this is what it's all about. This is our relative error. And if you want to turn it into a percentage error, you just make it over 100. Okay, so whatever that turns out to be, over 100. So let me just check my notes. That is everything I wanted for part 1. So I'm going to stop right there. All I got to do is figure out how to stop this. Let's see. Stop recording. All right, that's it for now.